Welcome to the second lecture of this week of EE557. In the last lecture we have seen the algorithm called Kalman filter, which is used for Bayesian estimation of linear Gaussian systems. In this lecture we are going to see some properties of it. There are six of them. So this was the algorithm we have written last time, and let us see the properties now. So I will abbreviate Kalman filter with the capital letters KF. Okay? So let us look at the first property. Property 1 says that the innovation sequence nu k, which is defined as yk minus y hat k given k minus 1. So this is true for k, 0, 1, etc., is an independent and zero mean stochastic process. So as you know, in the Kalman filter, in the measurement update step, we always calculate these quantities. So these are the innovations at time k, and by innovation we mean that yk minus it is expected value when all of the past measurements are given to us. So I have mu k is equal to yk minus y hat k given k minus 1, and we know that this is nothing but yk minus I have expected value yk given y0 k minus 1. Okay? And this property claims that this innovation sequence nu0, nu1 going until infinity. Here in the algorithm I continued until the final time n, but you don't have to. As long as you have measurements, you can continue this process indefinitely. Okay, so this sequence is zero mean, so it claims that we have expected value of nu I, or let us say nu k, is equal to 0, and also it claims that these are independent random vectors. Okay, in general y doesn't have to be a scalar, it's a vector, so innovation can be a vector. So these are zero mean and independent vectors. This is quite interesting. Such simple algorithm can actually generate infinitely many independent random vectors from quite correlated or dependent random measurements. Okay, so measurements are dependent with each other. So because they are dependent on the states, and states in time are dependent on each other, which means that the measurements are dependent on each other for all times. But the innovations that the filter calculates, they are not. They are independent of each other. Okay, so let us first try to see how we can see the zero mean property. I will just prove the zero mean property in two ways. There are two ways to prove it. Actually, we have already seen this innovation concept towards the beginning of the semester, and we have seen that this is a zero mean. This should be a zero mean sequence. Why is that? Because yk, in this case, when we have linear Gaussian systems, yk, xk, they are all Gaussian processes. Okay, so I can actually show that this is a zero mean random vector by using Gaussian process property. But here I'm not going to do that. Okay, so here let us try to prove that without knowing that this yk is a Gaussian. Let us try to show that this innovation sequence is zero mean. Okay, so here I can actually take the expected value of nu k. Okay, unconditional expected value. And this is going to be expected value of yk minus, I can write this expected value yk given y0 k minus 1. And now I can distribute this expected value into these two factors. So I have expected value yk minus expected value. Inside an expected value, there is another expected value. Expected value yk given y0 k minus 1. Okay? This is the first way to prove this. I will show you two ways, and the second way is going to be more important for us. So here you see that I have two expected values, but here you see an expectation inside an expectation. And inner expectation is with respect to the condition, inner expectation is with respect to yk, because the other ones are in the condition, and the outer expectation is with respect to y0 k minus 1. Okay? But we know by the law of iterated expectations, expected value x given y is a function of y, and when I take its expected value once more, this expectation is with respect to y, and this expectation is with respect to x. It would give me expected value with respect to x, like this. Okay? So here, this actually concentric expectations is nothing but y, expected value yk. And I have here expected value yk as well, so this is 0. So now this was the first way, probably the easier way to show that these innovations are zero mean. But here I'm going to do it in another way, okay? Because we are going to be doing this type of calculations in this lecture a lot. That is why I want to prove the same thing once more using a different idea. So expected value of nu k, I can actually write this as follows. Expected value, I can actually make things a little bit more difficult. I can put an inner expectation into this expectation, okay? But we are going to see why this is going to make things easier at the end. So expected value of nu k is equal to expected value of nu k given y0 k, okay? By this rule, I know that this is correct. Law of iterated expectations. Okay. Now let us try to. I will write the outer expectation directly, and I will write the inner expectation as follows. So I have yk minus. I have yet another expectation. Yk given y0 k minus 1. Okay, I have given y0, sorry, here I have y0 k minus 1. Okay, so I have here y0 k minus 1 in the inner expectation, and the outer expectation has no conditioning. Now I want you to concentrate on the inner expectation. I will distribute this expectation into the terms of the subtraction here. Okay, so I will write this as expected value yk. Of course, I need to keep the given conditioning, y0 k minus 1 minus expected value of yk given y0 k minus 1 given y0 k minus 1. Okay. So this is my inner expectation. If I add the outer one as well, I will obtain this. Okay? Now this is the expectation that we are subtracting here. It's the same expectation. And in this case, I have the expectation of the same expectation given y0 k minus 1. I told you that expected value x given y is a function of y. Okay? Because when you take an expectation like this, you actually get rid of all of the randomness of x except for the randomness in y in the given condition. So in general, this is a function of y. Okay? So as a result, this inner expectation here is a function of y0 k minus 1. Okay? But y0 k minus 1 is already given to us. Okay? That means that this quantity is deterministic given y0 k minus 1. So it is going to get out of the expectation directly. Okay, so I have the outer expectation like this, and this term remains as it is, yk given y0 k minus 1, and this inner expectation can get outside this outer expectation directly, because y0, when y0 to k minus 1 is given, this inner expectation is deterministic. Okay, expected value yk given y0 k minus 1. Okay, but these terms are canceling each other, so we end up with the expectation of just 0, which is 0. Okay. So this second way of showing the same thing in a longer way, we are going to be using in this lecture. Okay, so we show that the innovations are they are zero mean random vectors. Okay, so are they independent? Now we can actually use the Gaussianity property. Okay, I know that in a linear Gaussian system, all variables are jointly Gaussian. Okay, so that means that y0, y1 going until infinity are jointly Gaussian. Means that y0 to y0, y1 is a Gaussian process. That is the definition of a Gaussian process, being jointly Gaussian at all time instants. Okay? So y0, y1 going until infinity is a Gaussian stochastic process. But when we covered the topic of Gaussian processes or Gauss-Markov processes, we have seen that if you have a Gauss process, Z0, Z1 going until is an arbitrary Gaussian process, then the innovations that you define from those z variables as zk minus expected value zk given z0 k minus 1 are independent. Okay? So we have seen this in one of the earlier lectures towards the beginning of the semester in the past. So for any Gaussian process, we have the independence of this innovation process. Okay? Innovation process is independent of z0 to k minus 1, and furthermore, innovation process is independent. Innovation process at time k is independent from the innovation process values at earlier times. Okay? So I'm not going to prove this once more. We have already done this proof at that time in the earlier lecture. But we know that Y is a Gaussian process, and that means that its innovations should be independent. Okay? So I'm not going to give you any further proof here. So what does this mean? This means that the innovation process is independent. That means that expected value, innovation process at time I, times innovation process at time j, transpose. I am going to be assuming I not equal to j, okay? At different times, the innovation process values are independent from each other. That means that they are also uncorrelated. So here I can actually, so independence implies uncorrelatedness. That means that this expectation of this multiplication would be multiplication of the expectations due to uncorrelatedness, which comes from independence. Okay? But I know that these expectations are both equal to 0. We have already seen that the innovation process is zero mean. So you see that, and this is true for I not equal to j. For I not equal to j. Of course, when I is equal to j, this is going to be the expectation of a positive semi-definite matrix, which is going to be positive semi-definite. So So now when you look at this quantity, so I can actually do the inner product type of multiplication as well. Okay? If I have this quantity like this, then I can do the similar thing due to independence, and this is going to be 0 as well. This is matrix 0, this is scalar 0. Okay? But doesn't this look like an inner product here? So if I consider random vectors as vectors in a vector space, and if I define on that vector space an inner product, okay? So I can define an inner product like this, and this inner product takes two random vectors like this, and I can calculate their inner product like this, x transpose y. Okay, I can define an inner product like this, and in that case, this tells me that inner product of nu I and nu j is equal to 0 with this definition, inner product definition. But in that case, this means that nu I is orthogonal to nu j when I is not equal to j, for I not equal to j. Okay? So in some way, when you define an inner product in a linear space of random variables or random vectors, then you see that in that vector space, these innovation process variables, innovation vectors, are orthogonal to each other. Okay? So then what use is this? So think about then the Kalman filter as follows. Suppose that I think that, of course, Kalman filter for some finite n takes some measurements. Think that the Kalman filter returns you, gives you the output of nu 0n. Okay? So this is done by the Kalman filter. Think that the Kalman filter is an algorithm which takes these outputs, okay, as its input, and it gives you the output as the innovation process. Okay? So here, the interesting thing is that in general, we can think that the Kalman filter takes the measurements and gives us the state estimates as the outputs. But I want you to think about or consider the Kalman filter as an algorithm that takes takes the measurements as the input, and it gives you the innovations as the output. Okay? In that case, what do we have? The algorithm takes y0, y1, going until yn, and it returns to you nu 0, nu 1, going until nu n. Okay? And I know that this inner product of nu I, nu j is equal to 0 when I not equal to j. Okay? Or nu I is orthogonal to nu j when I is not equal to j. Okay? What can I say about the measurements? The measurements in general are not uncorrelated. They are not zero mean, and they are not independent, and even they are not uncorrelated with each other. So actually, if I look at this inner product yi, yj, in general, this is going to be non-zero, okay? So I can say that yi is not orthogonal to yj for all I not equal to j in general. So when you think that Kalman filter is an algorithm that takes these non-orthogonal vectors and it returns you, it gives you the output of these orthogonal vectors, which are obtained from the linear combinations of these non-orthogonal vectors. Okay? Does this remind you something? An algorithm which takes non-orthogonal vectors in general and it returns you a set of orthogonal vectors which have the same span as the original input variables here. Yes, this should so far remind you actually the so-called Gram-Schmidt algorithm. Gram-Schmidt algorithm takes non-orthogonal vectors, a set of vectors, a set of linearly independent vectors, if you will. Then it returns you some orthogonal vectors which are obtained from the linear combinations of the input vectors. Okay? So when you think about the Kalman filter as an algorithm like this, then it really resembles a Gram-Schmidt orthogonalization procedure. Okay? And in fact, one of the derivations of the Kalman filter in the literature is based on the Gram-Schmidt orthogonalization, with the inner product defined as I did in this lecture. Okay, so one of the derivations of the Kalman filter is based on the Gram-Schmidt procedure, and actually Kalman filter is a version of the Gram-Schmidt orthogonalization for random vectors. So this finishes the first property. Now we're ready for the second property. Property 2. Property 2 is more or less a verbal property. I will not be able to write it here completely. I can think about the Kalman gain K. Okay? So here we see that Kalman gain controls the effect of the measurements, so the innovations on the state estimate. Okay? If Kalman gain, it is actually a vector, or it might be a matrix, depending on the dimensions of the state and the measurement. Kalman gain in general controls the effect of the measurements on the state estimates. Okay? If Kalman gain elements if they are large, then the effects of the measurements on the estimates would be large. And if the Kalman gain elements are small, then there will be little effect of the measurements on the state estimates. Okay? And how about the covariances Q and R? Okay? In general, you have to be thinking about the Kalman filter as an information fuser. Okay? What does it mean? In Kalman filtering, we have two pieces of information. The first is state model, xk plus buk plus gwk, and the second piece of information is the measurement model. Okay? And I have h, vk. So a Kalman filter fuses these pieces of information, and it includes the information of the state model in time update, and it includes the information of the measurement model in the measurement update. And these covariances Q and R would determine how much Kalman filter trusts on these pieces of information. Okay? So here, if Q is large, that means that this noise in general is very large. Okay? That tells the Kalman filter that it shouldn't trust the state model. Okay? If R is very large, then that means that the measurements are quite noisy, and in that case, this R being large tells the Kalman filter that it shouldn't trust the measurements, or it shouldn't trust this measurement model. Okay? So then what can we say about the Kalman gain when Q is increased or it is decreased? So if Q is large, if Q is increased in a Kalman filter, this tells the Kalman filter that its trust to the state model should decrease. If a Kalman filter's trust is decreased to the state model, then its trust on the measurements would increase. So what does that mean? If Q is large, then Kalman filter will not trust this state model, okay? Because there can be anything here. This equation might not be satisfied at all with a very large noise. In that case, if Q is very large, that means that Kalman filter will not trust the state model, and it's going to put its trust into the measurements. That means that it's going to increase the effect of the measurements on the estimates. That means that when Q is increased, then the Kalman gain is going to get larger. Because in that case, the trust is not on the state model anymore, but the trust is going to be on the measurements, and then the Kalman filter is going to increase. Similarly, if Q is decreased, then this means that if Q is very small, for example, this equation is satisfied almost exactly. So the filter is going to put more trust into the state equation, and therefore it's going to reduce its trust on the measurement and the measurement equation. So in that case, Kalman gain is going to decrease. Okay? What about the relationship is more direct in the case of the measurement covariance. If I increase R and if I decrease R, if R is increased, then this is going to tell the filter that the measurements are very noisy. So it's not going to, it's going to want to make the Kalman gain small, so that noise doesn't enter into its estimates much. Okay? Similarly, if R is reduced, this is going to tell the filter that the measurements are quite clean of the noise. That means that these are good measurements, so it's going to want to increase the effect of the measurements on the estimates. Okay? So Kalman gain in that case is going to increase. So in some way there are two pieces of information which are competing with each other. And how much these pieces of information would affect the estimates is determined by the selection of Q and R. Okay? So for every selection, there is a different balance between these pieces of information. So this completes property 2. I didn't write much, but it's going to be in the notes. So let us go into property 3. The property 3 tells us that the covariances, sigma k given k, or sigma k plus 1 given k, and the Kalman gains, maybe I should write also the innovation covariance here. Sk and the Kalman gain kk are independent of the measurements. Independent of the input and the measurements. Inputs and the measurements. Okay? This is quite interesting. So, in a Kalman filter, whatever the value of the measurement can be exactly equal to 0. The measurement can be 10 to the power 10. It really doesn't matter for the Kalman filter. The covariance, whatever covariance at each step, whatever the measurement is going to be the same. Okay? So you see that the covariances here, they are not dependent on the values of yk. So the realization of yk does not change the value of the covariances. Okay? So there is no y dependence on the covariances, and we see that this Kalman gain calculation is also dependent on the covariances, but it is not dependent on yk. So whatever the value of the measurement yk, we will always have the same Kalman gain. The filter does not look at the value of yk and try to adjust the value of the Kalman gain based on the value of that measurement. Okay? This is caused by the Gaussianity. Okay? When actually, this is one of the bad properties of a Kalman filter. It is very sensitive to to outliers. If in the measurements, if you have some outliers, then your estimates are going to be bad, because the Kalman filter does not change the value of its Kalman gain based on the value of the measurements. All right? This is caused due to the Gaussianity. It's Gaussianity magic here. So in general, if you derive a Bayesian filter for a non-Gaussian noise distribution, then the covariance that you calculate and the gain that you calculate, or the update formula that you calculate, is going to be dependent on the value of the measurement. Okay? Here we don't have that property. So this is in some way bad because it makes the filter sensitive to outliers in the measurements, but somehow it is also good, because here, because the covariances do not depend on the actual value of the measurements, you can calculate the covariances offline before you collect any measurements. Okay? So you can calculate the covariances and the Kalman gains in an offline manner before you collect any measurements from the system. You can store them somewhere and you can use them when their time comes. Okay? This was actually quite useful for the use of Kalman filter in the space program in the 1960s. So people didn't have the computational powers for actually updating covariances real time as the measurements come, okay? But they had storage, so they could store the covariances beforehand by calculating them before the mission. So then they can use the covariances when the measurement comes. They can extract the corresponding covariance from the storage, and then they can use it then, okay? So this was one of the important properties of the Kalman filter. So now let us go into property 4. So we define a state estimation error. Okay, I will call this state estimation error as x tilde. In general, in estimation theory, when we define a variable with tilde, it is usually a form of error somehow. And actually, innovation, nu k, it is yk minus y hat k given k minus 1. Sometimes, instead of nu k, we show this innovation as y tilde k given k minus 1. Okay? So it is the error in the estimation of the output. Okay? So here property 4 first defines an estimation error. It is xk minus x hat k given k. So we take the kth updated estimate of the Kalman filter and we subtract it from the actual state value xk. And this becomes our estimation error at time k given the measurements from 0 to k. Okay? And property 4 claims something very, very important. The estimation error x tilde k given k is uncorrelated with an arbitrary function. Arbitrary function of, let me write this function as psi y0k of outputs y0k. Okay? So this is property 4. And it tells us that this estimation error vector is uncorrelated with any function. This is quite a strong claim. And it tells us that this estimation error is uncorrelated with any function of y0k. For example, it should be uncorrelated with y0. It should be uncorrelated with y0, y1, etc. Okay? or it should be uncorrelated with y0 square, if it is a scalar, okay? Any function of y0k that you can think of, all right? So now let us try to prove this. The first thing that I'm going to do is to write what I need to prove. So remember, the uncorrelatedness is nothing but a covariance expression. So covariance of x tilde k given k, and I have psi y0k should be equal to 0. Okay? I need to prove this. But we know also that there is an equivalent statement related to the expectations. And this equivalent statement would be expected value of x tilde k given k psi transpose y0k is equal to expected value x tilde k given k times expected value psi transpose y0k. These are equivalent statements, okay? So these two random vectors are uncorrelated if their cross covariance is equal to 0, or if their expectations can be if the expectation of their multiplication can be distributed into multiplication of expectations, okay? So I will try to prove the second one, okay? They are equivalent. So the first thing that I'm going to do is to show that this expected value is equal to 0. Okay? So claim expected value x tilde k given k is equal to 0. We see that x tilde k given k really looks like an innovation of some form. Okay, xk minus its expected value given some past. Okay, now let us try to prove it. So I have expected value x tilde k given k is expected value. I will write x tilde k given k given. I will add an additional expectation here, y0k. All right. I'm using the second method in this case. The first method is also possible here. So this is going to be expected value of xk given y0k. I distributed the inner expectation into this subtraction minus expected value xk. So this is nothing but expectation of xk given y0k, xk given y0k, given y0k. Okay? So we have this. But now we have the same thing as before here. Okay? So I have expectation of this thing remains as it is, expected value xk given y0k, minus this expectation is a function of y0k, and y0k is already given to us. I have to close the outer expectation bracket here. And y0k is already given to us. That means that this quantity can get outside the expectation directly. So it's going to be expected value xk given y0k. And I know that this is 0. Which means that this is expected value of 0, which is 0. Okay? So this estimation error of the Kalman filter has 0 mean. All right? If I was giving a course purely on estimation theory, then this would mean that the Kalman filter is unbiased. There is a terminology related to the estimators, unbiasedness, and in this case we can say that since this expectation is equal to 0, Kalman filter is unbiased in a Bayesian sense. Okay? So we have seen that this expectation is equal to 0, okay? So this expectation is 0, and when I multiply it with anything else, I'm going to get 0. So then all I have to prove is that expectation of x tilde times psi transpose is equal to 0. Okay? That is the thing that I have to prove to show that this x tilde is actually uncorrelated with an arbitrary function of the measurements y from 0 to k. Okay? So then what I have to prove is this. Expected value x tilde k given k psi transpose y0 k is equal to 0. I need to show this, and that is, there's nothing but the expression of the uncorrelatedness of x tilde with any function of the measurements y0 k. So now let us try to do this. Expected value x tilde k given k psi transpose y0 k here. I will apply my trick. I will add an additional expectation inside. Expectation, x tilde k given k, and psi transpose y0 k given y0 k, and I would have this. So now you see that in the inner expectation y0k is given to us, but psi transpose y0k is just a function of y0k. Okay? So, and it would be deterministic given this condition. Okay? That means that this psi transpose y0k can get outside. Okay? Expected value x tilde k given k times psi transpose y0 k, and I would have the, sorry, I've forgotten the conditioning in the inner expectation. So this would be like this, and given y0 k, and I would have psi transpose y0 k. This got outside the inner expectation because with these given conditions it's deterministic. Okay? So I have just like this. Now let us look at the inner expectation. We have already calculated the inner expectation actually. So this is expected value xk minus x at k given k. And instead of x at k given k, I can write expected value xk given y0 k. Okay? Given y0 k. This is the inner expectation. I will multiply it with psi transpose y0 k. And I will close the outer expectation. Okay? Now it's quite straightforward from this point on. Okay? This is expectation. This term becomes expected xk. We have already done this. y0k minus, when I take the expectation of this term given y0k, it's deterministic, it gets outside. xk y0k, there is a parenthesis here, and psi transpose y0k, and because this subtraction is equal to 0, the overall result is equal to 0. So we see that this estimation error of the Kalman filter is uncorrelated with all of the past and the current measurements of the filter. Okay? So that means that the estimator of the Kalman filter can summarize to the full extent all of the past and the current measurements. Because if there was still a correlation of the estimation error with the past and the current measurements, that means that there is still something to extract from the measurements. Okay? So this uncorrelatedness is actually is actually the reason that the Kalman filter estimate is quite good, because it can summarize all of the or it can extract all of the information related to the state from the past and the current measurements. Then the estimation error becomes uncorrelated with the past and the current measurements. If there was still a correlation with the estimation error and the past and the current measurements, then this would have meant that there is still something more to extract from the past and the current measurements to get a better estimate. Okay, but it's not the case for the Kalman filter estimate. Okay. So what we have proven here is that x tilde k given k, which is xk minus x at k given k, is uncorrelated with any function psi of y0k. Okay? So now we come to the optimality property of the Kalman filter, which we are going to derive by using this property. Okay? Let me erase these. So now let us write property 5. The estimate x at k given k, calculated by the Kalman filter, has the minimum mean square error, has the minimum mean square error. Minimum mean square error is abbreviated in estimation theory literature as MMSE. Okay? Minimum mean square error among all possible estimates psi hat of y0k of xk. Okay, so this is saying to us that Kalman filter estimate is optimal in some sense. Okay, and optimality is the cost of the optimality is mean square error. The first thing that I'm going to do is to define what mean square error would be. But before that, let me talk about what by an estimate of xk, an arbitrary estimate of xk would mean. In general, if you look at this recursion, you see that this xk given k hat calculated by the Kalman filter, you see that it's going to be a function of y0 to k. Okay? So xk given k is going to be a function, and actually it's going to be an affine function of y0 to k. So the estimate at time k, estimate x at k given k, is going to be a function of y0, y1, yk minus 1, and yk. Okay? So now in this property, we are thinking about any possible such estimate, any such function of an arbitrary function of y0k. Suppose that instead of running this type of recursion, I have taken the square of y0, cube of y1, and I have multiplied them somehow, okay? And I obtained a magical estimate for xk again, which is a function of y0 to k again, okay? So this property tells us that you can try anything, any function of y0 to k as an estimate of xk. The error that you are going to get at the end with that estimate is always going to be larger than or equal to the Kalman filter error. Okay? So that is a really impressive property of the Kalman filter, and that is the optimality property of the Kalman filter. So we know that we have actually calculated the error x tilde k given k, which is xk minus x at k given k. Okay? This is the error at time k. So what is square error? Square error is x tilde k given k, x tilde k given k, sorry, transpose. Okay? So this is square error. This is a positive semi-definite matrix of rank 1. Okay? And what is mean square error? Mean square error is the expectation of this. Expected value x tilde k given k, x tilde k given k transpose. This is mean square error. If x was a scalar, if the state vector was a scalar, instead of x transpose, I could have written x square if it was real. Okay? Then I could write x square, and it would be just error squared, and then I take the mean, which is expected value. This is ensemble mean or ensemble average. Okay? So this is the mean square error, and it's a matrix in general. So this is the mean square error matrix. Okay? So now, and this is the mean square error matrix, or MSE. Let us write MSE matrix. But when I say MSE, then I mean that this is the MSE matrix. This is the MSE matrix of the Kalman filter. And when I write this like this, xk minus x at k given k, and xk minus x at k given k transpose, and you really see that this is the error squared, and then I take the mean. Does this have a relationship with the covariance that the Kalman filter calculates? In general, an MSE is not going to be equal to sigma k given k for a general Bayesian filter. But for the Kalman filter, we can see that its MSE matrix is equal to that covariance. What is sigma k given k? Sigma k given k is the covariance of xk given y0k. In the covariance calculation, I have the conditioning. In the MSE calculation, I don't have any conditioning. Okay? So here, if I write this as an expectation, it would be xk minus x at k given k, xk minus x at k given k, because this is the expected value given y0k, given y0k. Okay? So this is the covariance that the Kalman filter calculates. Compare it with the MSE. This is the MSE at time k. MSE at time k of the Kalman filter estimate. So you see that in one of them I have the conditioning, in the second one I have no conditioning. Okay? So actually for any filter, if I think that these x at k given k can belong to other filters as well, then I cannot say that MSE is equal to that matrix. But for the Kalman filter, we're going to see that these two are equal to each other. Okay? So let us try to obtain the general expression. This MSE of k is equal to expected value. Now I'm going to add an inner expectation with the conditioning y0k. Okay? Expected value xk minus x at k given k, xk minus x at k given k transpose given y0k for the inner expectation, and the outer expectation is unconditional. Okay? But this is nothing but that covariance that the filter is calculating. So this is expected value covariance of, I have here xk given y0k. Okay? Here I have assumed that this x at k given k is actually the expectation of this of the xk given y0k. Okay? So if this estimate belongs to a general filter, and if it is not the conditional mean of the state, then in addition to this you need to add a bias term to this as well. Okay? So this expression is correct only when this state estimate is the expectation of the state given y0k. All right? So this is equal to, so I have here expectation of the covariance of xk given y0k, and I know that in Kalman filter this covariance is not really dependent on y0k. Okay? So this outer expectation is with respect to y0k, and the inner expectation is with respect to xk. Okay? So, and in Kalman filter, this covariance is not really a function of y0k. We have seen in one of the previous properties that Kalman filter covariance is independent of y0k. That means that this is going to be directly equal to covariance of xk given y0k for the Kalman filter estimate, and that is going to be sigma k given k. All right? So for the Kalman filter, this covariance that we calculate is equal to the MSE of the filter as well. Okay? But in general, MSE and that covariance for other estimators do not have to be equal. All right? I need to erase this. So now let us define the MSE of the other estimators. The MSE of the other estimators would be just this. This other estimator would be psi y0k, okay? And I will subtract it from xk, and then I will write the same thing, xk minus psi hat y0k, and transpose, and I will take the expected value. This is the MSE of the other estimators, okay? This is the MSE of the Kalman filter, and this is the MSE of the other estimator, or any possible estimator. Okay? So here, this property claims that MSE of the Kalman filter, so this expected value, xk minus x at k given k, xk minus x at k given k, transpose, is always smaller than or equal to this MSE. Okay? Expected value xk minus psi hat y0k, and xk minus psi hat y0k transpose. Okay? This is the MSE of the Kalman filter of kf, and this is MSE. Let me write subscript k here. MSE k of any possible estimator. Okay? That is what this property is claiming. Okay? So how to see this, or how to prove such a property? So here I'm going to give the proof. Let us write proof. So I will first define the error of an arbitrary estimator. Xk minus psi hat y0k. This is the error of an arbitrary estimator. And here is what I'm going to do. into this, I will subtract and add the Kalman filter estimate. Okay? I subtract the Kalman filter estimate, add the Kalman filter estimate, minus psi hat of y0k. Okay? So this error, the estimation error of an arbitrary estimate can be written like this. Kalman filter estimate error and the difference between these estimates. Okay? So now I can write this. Expected value xk minus psi hat y0k times the same thing transpose is equal to, I will write this thing and the same thing transpose. Expected value xk minus x at k given k plus x at k given k minus psi hat y0k, and I would write here the same thing transpose. I have this times the same thing transpose. Okay? So now let me distribute this outer product here. Okay? I will take these two terms together, and I will take these two terms together, and then I will distribute this outer product into these terms. Okay? So I would have expected value, this thing times its transpose, xk minus x at k given k, xk minus x at k given k, transpose, okay, plus this thing times the other thing's transpose, xk minus x at k given k, and I would have this thing transpose, x at k given k minus psi hat y0k transpose, okay? And I will go into the other term, plus expected value x at k given k minus psi hat y0k times this thing transpose, this term's transpose, xk minus x at k given k transpose, and finally this term and its transpose. Minus psi hat y0k times the same thing transpose, x at k given k minus psi hat y0k transpose. Okay? So now I have four terms. All right? Here on the left hand side I have the MMSE K of an arbitrary estimator. Arbitrary estimator. Psi hat y0k. Any function of the measurements y0k. Now let me try to look at these terms. I know that this first term is the MMSE of the Kalman filter. MMSE K of the Kalman filter. Okay? Now, I want you to concentrate on the second and the third terms. On the second term, this is my x tilde k given k. This xk minus x at k given k is x tilde k given k. Okay? And similarly here, this term is nothing but x tilde k given k. We have seen in the earlier property that this x tilde k given k, its expectation when it is multiplied with any function of y0k is equal to 0. Okay? We have already seen that expectation of x tilde k given k times any function, let me say f transpose of y0k would always be equal to 0. This is the uncorrelatedness property of the estimation error of the Kalman filter. Okay? So now look at the other term here. X at k given k is a function of y0k. It's the Kalman filter estimate, and it's a function of y0k. And this psi hat y0k is a function of y0k, but we see that this subtraction should be also another function of y0k. And it is multiplied by x tilde k given k, and we take expectation. That means that this expectation is going to be equal to 0. The third expectation is just the transpose of the second expectation here. So transpose of a 0 matrix is 0. So I have this. All right? And what can I say about the last expectation? I have a quantity, a difference here, times that same quantity transposed. Okay? So this is in some way a covariance matrix. Okay? So it is the expectation of a positive semi-definite matrix. Expectation of a positive semi-definite matrix. Which means that this last term here is always larger than or equal to 0 in the positive semi-definite sense. Okay? But then what does this give us? MMSE k of an arbitrary estimator is equal to MMSE k of Kalman filter plus a matrix which is positive semi-definite plus a matrix which is positive semi-definite. What does this mean? This means that if I compare these two quantities, this is always going to be larger than or equal to this one. Okay? So if I erase this thing, and if I erase this equality, then we will always have this. So we see that the MMSE k of the Kalman filter is always smaller than or equal to MMSE of an arbitrary estimator. So Kalman filter estimate is the best that you can do in terms of in MMSE sense actually. Okay? So just for this reason, I will just write a remark here. For this reason, Kalman filter is the minimum mean square error estimator. Minimum mean square error estimator for linear Gaussian systems. So it is the best estimator in mean square error sense. And we have just one final property that we are going to see. It is property 6. And it tells us that Kalman filter is a time-varying filter. This is really simple. If you look at the equation here, connecting the states, connecting the measurements to the state estimates, we see that the relationship between the measurements and the states is determined by this coefficient, Kalman gain, which is kk. And this k sub k, we see that it is dependent on time. Okay? This Kalman gain is dependent on time. That means that the relationship between the input of the filter, which are the measurements, and the output of the filter, which are the state estimates, the relationship changes in time. The relationship is dependent on time explicitly. Okay? And that means that the Kalman filter is a time-varying filter in general. But this is not really surprising, right? Because a linear Gaussian system, xk, xk plus 1, axk plus buk plus gwk. For a linear Gaussian system, the mean of the state is changing with the input, and plus the covariance of xk is changing. So state process is actually a non-stationary process. Similarly, the output of the system is also a non-stationary stochastic process. So it is quite natural that the filter, the optimal filter that we find at the end, is also time varying or non-stationary. Okay? So Kalman filter is actually a time varying filter, but sometimes if some conditions are satisfied, then these covariances, sigma k given k and sigma k plus 1 given k, if some conditions are satisfied, when we run this filter for a long time, then these covariances would converge to some constant covariances. Okay? Of course, when the covariances settle at some steady state values, then this Kalman gain settles at some steady state value. Okay? And in that case, the Kalman filter turns into a time invariant filter. Okay? Which is called a steady state Kalman filter. Okay? So we are going to see the conditions for such a convergence of the covariances to some constant values. And actually, if the process is stationary, and when the Kalman filter goes to a steady state filter, that filter actually becomes the so-called Wiener filter that is studied in signal processing. So Kalman filter is actually the generalization of Wiener filter to non-stationary processes. Wiener filter appears quite widely in signal processing and telecommunications, and Wiener filter is based on the stationarity assumption of the stochastic processes that we deal with. And a Kalman filter is by definition defined for a non-stationary process. Okay? But if the process is asymptotically stationary, and if the conditions of the convergence of the Kalman filter to the steady state are satisfied, in that case, the Kalman filter reduces to a time invariant filter, and since the process turned into a stationary process as well asymptotically, that filter actually becomes the so-called Wiener filter, which is a special case of the Kalman filter. So Kalman filter is nothing but the generalization of a Wiener filter to non-stationary processes. So that is all that I will talk about the Kalman filter properties. In the next lecture, we are going to see this convergence issue, and then I will have to remove some topics from the course. So I was planning to consider the control of Markov chains and linear Gaussian systems with partial information, and it seems that since I don't have enough lecture hours left, I will have to remove one of these topics. So I will reduce the content of the course a little bit. That's all for this lecture. Thank you very much for watching. Bye.